Let's continue with 9.8, example 2. This is power series. Find the radius of convergence and the interval of convergence. Be sure to check the endpoints. So here we have f of x equals the summation of negative 1 to the n plus 1, x minus 5 to the n, all over n times 2 to the n. Now this portion is only the alternator. So this alternator only contributes to the sign, not the magnitude of the expression. So this is only responsible for changing the sign of each term from negative to positive, and so on and so forth. So we're going to use the ratio test because we're dealing with exponents. So we also have absolute value, which means that we can drop this out. It's not going to be a factor within our ratio test. So we just take it out since it's always going to be positive inside. The result of the absolute value will always produce positive. Okay, so the first portion of the ratio test, we're going to replace all the n's with n plus 1. So x minus 5 to the n plus 1 over n plus 1 times 2 to the n plus 1 divided by a sub n. Divided by a sub n is the same thing as multiplying by the reciprocal of the rule of sequence. So n times 2 to the n will go up top, and the bottom will be x minus 5 to the n. Okay. Now we're going to have an easier time to simplify rather than having to look at a complex fraction. And we see that we can cancel out the x minus 5 to the n, which leaves us with x minus 5. N over n plus 1 is here. And then 2 to the n over 2 to the n plus 1 will give us just 2 in the denominator. Now, if we evaluate this limit as it approaches infinity, n over n plus 1, the degrees are the same, so this will just cancel out to be just 1, leaving us with x minus 5, absolute value of x minus 5 over 2. And we know that this series will converge as long as this expression is less than 1, since that's the condition for our ratio test. Okay, so from here, we are going to multiply both sides by 2 and eventually solve for x. So we get absolute value of x minus 5 as less than r. Now notice that this matches nicely with the form of absolute value of x minus c is less than r, which means that our center is at 5 and our radius is at 2. So we know that our center is at 5, and then we can use the radius to help us determine where the lower and the upper bounds are for our interval of convergence. Radius is 2, center is 5, so from 2, we're going to go to the left 5 units. Sorry, from the center of 5, we're going to go to the left 2 units, and then from the center, we're going to go to the right 2 units. So that gives us a possible interval of convergence from 3 to 7. Now, this is only the potential interval of convergence because we have to also consider the endpoints. So this series may or may not converge at 3, and it may or may not converge at 7. If it does not converge at 3, we have to use parentheses. If it does converge at 3, we're going to have to use the bracket for our interval. Okay, so let's test 7 first. So if we test 7, what we do is we take x equals 7 and we replace 7 in for the original rule of sequence that they give us in the problem. So the x gets replaced with 7, and then we're going to clean this up and see if this will produce something that converges or diverges. Okay, so I'm going to copy down the rule of sequence exactly as is. Negative 1 to the n plus 1, replace the x with 7 minus 5 to the n over n times 2 to the n. 7 minus 5 is 2. Now 2 to the n will cancel out. This leaves us with negative 1 to the n plus 1 over n. Now this is normally a harmonic series, and a harmonic series we know that it usually diverges. However, this is a alternating harmonic series. If alternating harmonic series, we know that will converge. It does approach 0 fast enough, so this will converge. And so if it converges, we know that for 7, we're going to include a bracket because at 7, the series will converge. Okay, let's test the other endpoint, x equals 3. Replace 3 in for the x from the original rule of sequence. So this gets me 3 minus 5 to the n. And then copy the rest of the rule of sequence from the original. So negative 1 to the n plus 1, 3 minus 5 is negative 2 to the n over n times 2 to the n. Now, I'm going to try and cancel out the 2 to the n, but first I'm going to take out the negative 1 to the n. Now the 2 to the n cancels out. I'm going to combine this by adding exponents. So n plus 1 plus n gives me 2n plus 1. And let's see what happens here. Negative 1 to 2n plus 1 over n. This is actually not going to alternate because 2n plus 1 will produce odd numbers. Right? Start off with 1, then we get 3, then we get 5, then we get 7. If we have a negative number raised to an odd number, it'll always produce a negative number. So that's the same thing as saying negative 1 over n. Negative 1 over n is basically a negative harmonic series. That negative is not going to alternate signs. So we know that this is just going to diverge. If it diverges, therefore, we know that 3 cannot be included as part of the interval of convergence, so we have to put a parentheses around the 3. Okay, let's look at example B, or part B from example 2. Summation of parentheses x over 3 to the n. I can clean this up by making it x to the n over 3 to the n. Again, we have exponents, so we're going to find the radius convergence, interval of convergence using the ratio test. A sub n plus 1 goes up top, or comes first. Replace all the n's with n plus 1. Divided by a sub n, which is the same thing as multiplying by the reciprocal of the rule of sequence. So 3 to the n over x to the n. Cancel out, we get x over 3. We know as long as this expression is less than 1, we know that this series will converge. Solve for x, multiply both sides by 3. Absolute value of x is less than 3. We can match this with x minus c is less than r. Therefore, the c must be 0. The radius is 3. So the center is at 0, and we have to go left 3 units to get to our lower bound and right 3 units to get to our upper bound. From here, we do parentheses bracket to indicate that we have to go ahead and make sure that we test the endpoints. So let's test negative 3 first. We're going to take replace the x with negative 3 from the original rule of sequence. So negative 3 to the n over 3 to the n. That's the same thing as negative 1 to the n. Negative 1 to the n will just, if we write out the first few terms of the sequence, we're going to see it's going to be 1, minus 1, plus 1, minus 1, plus 1. So we see that this series will keep diverging from a sum of 1 to 0 to 1 to 0. So it's never going to settle on a value. So by the nth term test, the series will diverge. If it diverges, we know we can't include negative. We use parentheses around negative 3. Now to test 3, going back to our original rule of sequence, replace x with 3. 3 over 3 is 1, 1 to the n. This also diverges by the nth term test, because if we test the first few terms, we get 1 plus 1 plus 1 plus 1, which will increase to infinity. It will not converge. Therefore, both our endpoints are going to diverge. We put parentheses around them. We could also use the root test to show that to solve for x. And then also another thing to kind of consider is that we are basically looking at a geometric series. And with a geometric series, we know that no matter what, our endpoints will never converge. So that's another indication that our endpoints will remain as negative 3 is less than x is less than 3. Okay, let's look at the rest of example 2 with part C and D on the next page. Okay, again, we go straight to our ratio test. Replace all the n's with n plus 1. When we do that, we have to do a little bit of distribution here, multiplied by the reciprocal of the original rule of sequence. Again, we leave out the negative 1 to the n. That's just an alternator, which will be irrelevant inside the absolute value bars. Okay, 2n plus 2 plus 1 is 2n plus 3. And then we look to see if we can cancel out. Here we can cancel out everything except for the numerator will remain with x cubed over x to the first power, which is x squared. 2n plus 1 and 2n plus 3 factorial. This is the same thing as 2n plus 3 times 2n plus 2 times 2n plus 1. Once you get down to 2n plus 1, it will cancel out with the numerator, which leaves the denominator with 2n plus 3 times 2n plus 2. All right, now limit as n approaches infinity. We see this is going to be n squared. The limit is always less than 1 regardless of what x is. So we know that this is going to increase a lot faster than this static value. So this expression will always be less than 1 because it will always come out to be 0, since this fraction will get closer and closer to 0. So therefore our radius is infinity, our interval of convergence is from negative to positive infinity, and our center is at 0. Okay, part D, summation of n factorial, x minus 3 to the n. Now, just to kind of note here, if a rule of sequence does not go towards 0, then the series basically has no chance of converging. N factorial, there's no way that this n factorial, there's nothing in the denominator. So this expression is just going to go directly to infinity. So we can go through and test using the ratio test. And also, when we do that, we can also confirm that there's no way that this will converge. No matter what the n value is, this will, no matter what the x value is, this will always go to infinity. Infinity is greater than 1. There's radius of 0. There's no interval of convergence. However, remember that even though there's radius of 0, remember condition 1 from when we first started the lesson, that the series will converge always at the center. So we can say that the series will converge at 3, since 3 is the center. It just won't converge for any other values. Okay, here we have Taylor series, and Taylor series is basically a power series, but it has this pattern. And the pattern here is the first two terms is basically a tangent line equation, and then we follow a pattern of using the second derivative evaluated at c over 2 factorial, and then so on and so forth until we get to the nth derivative evaluated at c over n factorial times x minus c to the n. Hey, notice how we're using the equal sign instead of an approximation sign, and the reason why is because we have infinitely many terms. If we have this plus dot dot dot, we know that it will go to infinity, which means that this series will match exactly with the original function.